Hello and welcome back. We will pick up where we left off last time, which is looking at critical values in hypothesis testing. So to reiterate, in an hypothesis test, what we were looking to do is test whether or not a claim is true or false by looking at a sample. And that sample, when we look at the value for that sample, the value will either be very unusual, in which case we can reject what's called the null hypothesis, or the value is not unusual, in which case we cannot reject the null hypothesis. So how do we determine when something is unusual and when something isn't? Well, we look at the critical region, and one way to determine the critical region is to find the critical values. So our test statistic is going to be distributed either with a normal distribution, the student t distribution, or the chi-squared distribution, depending on what kind you're looking at. So for instance here, if we're looking at a proportion, this will be normally distributed. And our significance level is going to indicate the area, the amount of area for which our test statistic will be unusual. So if we happen to lie in the critical region, this is going to be considered an unusual value, and we can reject the null hypothesis. So this is where, this is the critical region. And the critical value is just this value that separates the non-rejection region, the non-critical region, from the critical region. So this is the critical value. And our test statistic will either fall to the left of this value or to the right inside of the critical region. Now, this particular graph would be used for when the alternative hypothesis is looking at a proportion that's greater than some number. But we could be looking at a situation where we have the proportion is less than some number. And if it's less, we're going to have a critical region that is a left tail. So here, our critical value is just going to be to the left of the center, and the tail will extend to the left. The last case is when p is simply just not equal to something. So it could either be bigger or smaller, and in which case we will have two critical regions, one extending to the left and one extending to the right. And then we'll have two critical values, one on either side. But because, for instance, the normal distribution is symmetric, we'll have the same critical value on both sides. One is positive and negative. However, if you think back to the chi-squared distribution for standard deviations and variances, that is not symmetric, so it won't be quite as nice, and you'll just have to figure out two different critical values. So essentially, we're just looking to see whether or not our test statistic falls in the critical region or not. And if the test statistic is in the critical region, i.e. the rejection region, we reject the null hypothesis, and essentially the test statistic extends past the critical value in some sense. Or it could be that the test statistic is not in the critical region, in which case we'll just fail to reject HO. So in this case, our test statistic is not so unusual that it couldn't have happened by chance. In which case we can't reach any conclusions. Now, wording the final conclusion. This was something that we mentioned a while back, in that we want to phrase things in a way that is going to be understood, is going to be clear for someone who's not versed in, say, statistics, to be able to read. So there's a couple different scenarios. Either we reject the hypothesis or we fail to reject the hypothesis. And the null hypothesis is the hypothesis that includes equality. So our original claim could be the null hypothesis, as in it could include equality in there, or it might not include equality. So for instance, if the original claim doesn't include equality, and we reject H0, we would say that there is sufficient evidence to support the claim that blah, blah, blah. So because our original claim doesn't include equality, our claim is going to be the alternative hypothesis. And when we think about the difference between the null hypothesis and the alternative hypothesis, if the null hypothesis is not true, it must be the alternative hypothesis, which would mean that there is sufficient evidence to support our claim. Okay. However, maybe we can't reject the null hypothesis. Maybe we can't say that H0 is false. So it could be true. Who knows? We didn't find anything so unusual that we could reject this hypothesis. This could be true. This could be true. So what do we say? There is not sufficient evidence to support our claim. And that's it. All we can do is we can say that we can't reach the conclusion that our claim was true or claim was false. We simply do not have sufficient evidence. Okay. So, however, our initial claim could include equality. So our initial claim could be the null hypothesis. So in this case, if our claim was that H0 is true, and we reject it, well, then we can just say that there is sufficient evidence to reject our claim. And that's it. So if we're claiming that H0, the null hypothesis is true, but we reject it, we just say so. There is sufficient evidence to reject the claim that, and then you explain, to reject our claim. And then the final case is that if our claim was H0 or included H0, and we failed to reject it, we have to say so. There wasn't enough evidence, there was not sufficient evidence to reject our claim. So let's put this into practice. So in our example that we've been looking at through the last couple of videos, we said that the proportion of people who are uncomfortable with drone deliveries is greater than half the population. So the proportion was greater than 0.5. And we found that we rejected H0, the null hypothesis. And the null hypothesis, just so that we remember, was that P was equal to 0.5, as in the proportion of people that are uncomfortable with drone deliveries is exactly 0.5. Well, we rejected that. So, since we rejected this, we can say that there is enough evidence to support the alternative hypothesis that a majority of people are uncomfortable with drone deliveries. Okay, so because it doesn't include equality, it's got to be this. So we did find enough evidence to support our claim. And that's hypothesis testing in a very, very long nutshell. This is something that is important, and we're going to spend the entire rest of the chapter on this. So this is something that we will do enough questions, enough problems to be able to learn this. One very brief thing that I want to mention is just types of errors. So there are type 1 errors and type 2 errors. And when this is phrased in terms of the null hypothesis, if something is true, but we think it's false, as in if the null hypothesis was true, but we rejected it, we said, no, this is wrong, we made an error, and that is called a type 1 error. This alpha, this significance level, is the probability that we make a type 1 error. If instead the null hypothesis was false and we correctly said it's false, well, we're correct, and there's nothing more to be said. If the null hypothesis was true and we couldn't say that it was false, well, we didn't make a mistake. We didn't say it was false, so everything's all good. However, it could be that the null hypothesis was false, but we couldn't say so. Maybe the null hypothesis is false, but we suspect that it's actually true. This is called a type 2 error, and the probability that we get a type 2 error is called beta. And this wasn't directly used in any of our calculations. So there are different types of errors, and depending on the situation, a type 1 error might be a lot worse than a type 2 error, or vice versa. So depending on the situation, we may want to minimize alpha, the probability that this happens, or we may want to minimize the probability that we get a type 2 error, minimize beta. And that's just a brief overview of errors. What I'll do to finish up the time, I will look at just a quick example, and I'll go through exactly what we would do to sort of state our hypotheses and reject claims or fail to reject claims. So I claim the average resting heartbeat of an adult male is less than 70 beats per minute. And then in a study of 105 participants, the average heartbeat was 65, and the standard deviation was 5 beats per minute. So the initial claim, if I write this down using more technical jargon, this would be, I'm claiming that the average, as in the mean resting heartbeat, is less than 70. So this is my claim. So once I know the claim, I can write down my null hypothesis and my alternative hypothesis. My null hypothesis is going to be that mu is in fact exactly equal to 70. And the alternative hypothesis is going to be that mu is not equal to 70, but this is what I'm trying to test. So my alternative hypothesis is going to be that mu is less than 70. So far, so good. Next, I need to determine my significance level, and this can be anything that we want. It doesn't specify so in a question, so I'll use sort of the standard significance level of 0.05. Next, we need to determine our test statistic. So because we are looking at averages, and we don't know the standard deviation of the entire population, we are going to use the t-test statistic. And in this instance, this is going to be the population, the sample average minus the population, what we expect the population average to be, according to our null hypothesis, divided by the sample standard deviation divided by our sample size. So plugging all this in, this is 65 minus 70 over 5 divided by 105. And this is approximately equal to negative 10.25.